more than one Rydberg atom, we might be interested in understanding how they interact in order, for example, to promote or to create quantum gates, which are the basis of digital quantum computation. So the basic ingredient or the building block is now called the Rydberg blockade. Now, suppose that you have two atoms at distance r. The typical interaction strength scales like a van der Waals interaction as 1 over r to the 6, where r is the distance between the particles. So if we put the two atoms sufficiently far apart, we can induce simultaneous transitions from the ground to the Rydberg state. However, if the two atoms are sufficiently close, the interaction shift between the two particles, between the two levels, inhibits the simultaneous excitation of two atoms in the Rydberg state. And this is essentially the effect of the phenomenon of the blockade. Now, the blockade takes place at distances which are smaller than a critical distance called the blockade radius. And it is essentially very similar to what in condensed matter people called the Coulomb blockade. Now, suppose that instead we want to scale up our neutral atom quantum computer, and we want to start playing with many particles. So what we can do here is first start creating two reservoirs, which are these two regions here, where we trap the atoms with the very tightly focused laser beams, which are called optical tweezers. And then we start moving these optical tweezers in this central region, which is our processing units. And we can do it row by row. As you can see, atoms start to slide toward the central region. Okay. Now we might wonder which type of applications we can play with these large number of particles, where the number of particles can be of the order from few tens to few hundreds of particles, and possibly in the future even few tens of thousands of particles. And as you can see here, we can first think about this full quantum computing stack by first loading the atoms. Here it's quite complicated to point at the right part of the slide. So we first load stochastically, which means that we start filling these tweezers with a probability of the order of 60 to 70%. And then we rearrange these tweezers to create a certain geometry, in this case, just a square lattice. And then we start running the dynamics with the native unitary evolution of our processor. And finally, we perform some readout, basically projecting the state either in the ground or into the Rydberg state. And what you can see here is essentially a snapshot of a simulation, of a quantum simulation, of a square lattice driven with the native Rydberg Hamiltonian, and it ends up into what is called a checkerboard lattice. Now, as a first type of application, I would like to talk about the original idea that was put forward by a very famous physicist, Richard Feynman, back in the 80s, which is the idea of quantum simulation. So the basic idea of quantum simulation is to map a complicated quantum mechanical problem in terms of another tunable and controllable quantum mechanical problem that can be realized in the lab. So as a prototypical example, you might think at a problem in condensed matter, which is the so-called Fermi-Hubbard model in either 2 or 3 dimensions. So nowadays, there are realizations of neutral atom platforms of neutral particles in optical lattices, which is a slightly different type of technology than the one that I'm discussing today, where people can indeed realize or do quantum simulations of the so-called Fermi-Hubbard model. Now, quantum simulation has different types of applications in several fields, starting from quantum math that I just mentioned, but also high energy physics or cosmology, atomic physics, quantum chemistry, and then hopefully also quantum biology, as we will probably hear during this workshop. And it tackled this problem in 2 different directions. The first one can be to simulate the evolution of certain time-dependent Hamiltonian, and therefore to understand, for example, some response of our quantum mechanical system, or alternatively, to find the low energy properties of some complicated quantum system, to discover, for example, certain exotic quantum phases of matter, or in the context of quantum chemistry, to compute the molecular ground states of certain complicated molecular complexes. There are two ways to perform quantum simulations. The first, and probably the most well-known in the community of quantum computation, is the so-called digital one. Suppose that we start from a certain quantum state at a time equal to 0, and we want to obtain the quantum state of our quantum mechanical system at time t. So the whole idea is to basically perform a procedure which is called technically trotterization, which means dividing the quantum evolution in very small time steps and perform this quantum evolution sequentially by mapping the problem into a relatively complex set of quantum gates. And this whole sequence of quantum gates is called a circuit, very similar to what our laptops or clusters do in the classical computation. But this is actually a sequence of purely quantum gates. Now, the alternative way is the so-called analog quantum computation, where we replace this bunch of gates and this very complicated circuit in terms of the evolution of our quantum mechanical system in terms of the native Hamiltonian or the native dynamics of our complicated device. So in the case of Rydberg atoms that I was discussing at the very beginning, there are two different ways to perform these analog quantum simulations in terms of what are called two Hamiltonians. For those who don't know what an Hamiltonian is, you can just think about the energy function of a system. And there are two ways to, as I said, to realize these simulations. The first one is to map or to evolve our quantum mechanical system in terms of an Hamiltonian, which is very, very famous in the context of statistical mechanics, which is the Ising Hamiltonian. In this particular case, this is a long-range Ising Hamiltonian, where the interaction is the usual van der Waals interaction I was talking about before, and which is represented by this term here. The second one is an XY type of Hamiltonian, which is actually famous also in the context of chemistry or biology, to understand and characterize the transport of energy excitations in molecular complexes, where now the interaction scales like a dipole-dipole interaction as 1 over r cube, and it is also anisotropic. Now, if we want to start applying these, basically all this technique of analog quantum computation to solve some practical problem, we can start thinking about the simplest problem, which is the so-called adiabatic state preparation, which basically consists in starting from a well-known energy, or actually a well-known state of our system, for example, the ground state, of a specific Hamiltonian that we call H1 at time T1, and try to end up into an unknown state of a target Hamiltonian H2 at time T2. So how can we do that? Well, quantum mechanically, we can exploit a very famous result, which is called the adiabatic theorem, which basically consists in parametrizing an Hamiltonian H in terms of a parameter T that connects at time T1 and T2 to the original and the target Hamiltonian H1 and H2. So if we do this evolution sufficiently slowly, then we can guarantee that throughout all the evolution, we start from the ground state at time T1 and we end up into the ground state at time T2. There are some examples that I just wanted to show you that come from some experiments that have been performed first at Harvard a few months ago, actually in 2021, but there are also other results from different groups to which I contributed, where basically what you see here again is the previous snapshots. So you start from a complete or a fully loaded square lattice, and at the end of the evolution, for certain values of the Rabi frequency and the detuning, you end up into a checkerboard lattice. To be even more specific, one can even consider to map out the full phase diagram of this Hamiltonian, In terms of the detuning, small delta here is just this capital delta, and the blockade radius that I introduced before. And you see here that the phase diagram is sufficiently rich. It consists of several phases, including our checkerboard phase, an intermediate striated phase, which is a purely quantum phase, and then a start phase, a so-called star phase for large interactions. Now, of course, I don't want to go too much into the details, but let me instead talk about the second category of problems that can be addressed with these type of platforms, which are so-called optimization problems. Native types of optimization problems that can be solved by these platforms are so-called the maximum independent set. So if we take a generic graph, so let me tell you that these maximum independent set problems have applications both actually for transportation problems like traffic optimization, but also telecommunications like antenna placement, or logistics like channel allocation. And for you to have an idea of what this maximum independent set actually means, this is a purely mathematical problem. If we start from a generic graph, finding the maximum independent set means to identify the largest subset of this graph such that no two nodes of the set are adjacent. Now, if I ask you to find an independent set of this graph, well, there are several possible answers. So a very simple choice can be, for example, this side here and this side here. This is certainly an independent set because these two vertices, these two these two nodes are not connected by an edge, but it is certainly not the maximum size of an independent set. If we take a look closer to this graph, we end up with this solution. For example, this is not unique, but it's just one possible solution. And you can see that the dimension of the maximum independent set is given by 6 red dots. And now we might wonder, okay, but what does this graph have to do with the original platform of Rydberg atoms that I was talking a couple of minutes ago? Well, one possible way is to identify these white dots here, these white nodes, with the ground state atoms, and the red nodes with the Rydberg atoms, and actually identify that this graph can be built out of some Rydberg blockade constraint, so the same circle that you were having a look at a couple of minutes ago, and considering the fact that the Rydberg blockade is essentially an independent set constraint in the low energy subspace of this Hamiltonian here, so this energy function that I introduced a couple of minutes ago. Now, the cost function to minimize in order to find the so-called maximum independent set is just a purely classical problem. It's just a purely classical Ising problem that is composed, that basically contains as you can see, two different terms. The first one is a repulsive term in terms that is essentially a van der Waals interaction between different Rydberg atoms. And the first term here is the energy mismatch between the ground and the excited states, so the so-called laser detuning. And by switching on and off for different time intervals, these quantum term, so what is called the transverse field proportional to the Rabi frequency, we end up into different quantum states that we can then post-process from the purely classical point of view in such a way that we will be able to identify possible independent set, and eventually, by repeating this several times, the maximum independent set. So what you can see is that by using these purely analog quantum computational devices, we are actually able to solve practical problems, or at least to map practical classical problems in a quantum device. So let me tell you that the game is not over. This technology is rapidly evolving. And in principle, we will be able also to scale up the system up to a few tens of thousands of qubits, and possibly even going into the direction of really digital quantum computation by applying, for example, by using two different species, like, for example, rubidium and cesium, where the rubidium can be, for example, mapped into what is called the physical qubit, and cesium can be, for example, an ancillary qubits, which is the usual way, for example, to perform quantum error correction in quantum computation. The other possible way to proceed, and this is actually something that both Harvard and Quera are actually very interested in, is this so-called qubit shuttling or moving atom architecture. So what you see here is that during the time evolution with our Rydberg Hamiltonian, we can actually move the atoms in different parts of our lattice. So what are the implications of that? Well, you can think, for example, of performing some very simple entanglement transport experiments. So you first take two atoms and make it sufficiently close by in such a way that you can create an entangling gate like a C0 between the two of them, and then moving them far apart and try to see whether the entanglement between these two particles is indeed preserved at very large distances. The other thing that probably matches very well with the content of this workshop is related to possible applications in terms of NMR, and in particular to simulate what is called the free induction decay of molecular energy spectra. This is an experiment, the results of some experiment performed on trapped ions. So it's purely digital type of quantum simulation with a platform of IonQ, which is another quantum company based in the US. But similar type of Hamiltonian engineering. Here, what you see is just a purely Heisenberg model in the presence of a transverse field. And the type of dynamics, of spin dynamics that we are simulating is associated to this complex here that contains a carbon atom and 3 hydrogen atoms. Of course, this is extremely simple. It is just, of course, a toy model, but it can be scaled up with the use of these technologies to a few tens and possibly hundreds of individual components. So to conclude, let me show you what is the timeline for the development of this technology. So this technology started initially with a group of physicists both at Harvard and MIT back in 2015. Then in 2017, they were able to trap and control up to 51 atoms. In 2019, this spin-off called Quera Computing was created. And then in 2021, the first 256 qubit machine to realize analog quantum simulation came to the light. And a couple of weeks ago, we were able to put this machine on the cloud. So all of you guys can play with the same things that I was talking to you today. You can find basically our machine, which is called Aquila, on AWS Bracket, which is a platform served by AWS, so by Amazon, which you can access freely by gaining some credits from Amazon. If you're interested, you can talk to me. I can try to help you set up your account, and then you can start playing and enjoying the benefits of quantum computation with our analog devices. So with this, I would like to conclude and thank you for your attention.